Hello, welcome back to Mastering Statistics. We're going to switch gears just a little bit. We're going to continue talking about the correlation coefficient, but we're going to talk about the statistical significance of it. And what I mean by that is we're going to talk about how sure we are that there's some kind of a linear relationship between two variables. I'm going to say here in the beginning that some of what we're going to end up talking about in this lesson is going to be very, very close to some of the other stuff we've talked about before, but it's just going to be applying a few numbers to some of the ideas that I've already kind of brought up with you. So if it seems familiar, it's because I've already kind of talked about some of it before. So first of all, let's revisit the correlation coefficient. Here you have some variables we plotted on a scatter plot, pretty close to the line that we would be able to draw, the best line through there. And this is a positive slope type of relationship. This is a negative slope type of relationship. So this is kind of review. But remember, as, let me go and write it down here, as R approaches 1, gets closer and closer and closer to 1, then we get a graph that looks kind of like this, where the points are closer and closer and closer to that perfect line. If we ever get the correlation coefficient to equal 1, then every single one of our data points will actually fall directly on the line in a straight line. And the same sort of thing over here. Actually, I can't even spell. What I'm trying to say is as R goes to 1. Now, as R goes to -1, you get a situation that looks like this one over here, where you have the negative slope relationship. Remember, negative correlation coefficients mean a negative slope, a downhill sort of rolling, like a ball can roll down the hill type of slope. So as R is negative and gets larger and larger in the negative sense towards -1, the points are going to get closer and closer on average to this line. And if we ever could get the correlation coefficient to equal -1 exactly, then every one of our data points would fall on that line. So that's, in review, what it basically means. So in a nutshell, in a big picture, if you're studying some data and you have a really large negative correlation coefficient, then you're going to be pretty sure that there's a linear relationship, because all of these points are going to be really close to a line, right? And on the positive side, as R gets bigger and bigger, if you collect a bunch of data points that are really close to this line, and R is, of course, large, close to 1, you're going to be really sure, very high, let's say, level of confidence. Your level of confidence is going to be really high that there is a linear relationship. Because don't forget, these data points are plotted here and you're collecting data. It could actually be due to random chance that they fall on a line. That's something you need to kind of keep in the back of your mind. It is possible. I mean, lightning strikes. The odds of a lightning strike is really low, but it happens, right? So if I'm really unlucky and I sample 1,000 people and I get a bunch of points and they happen to fall pretty close on a line by total chance, then I'm going to draw the conclusion that these two variables are related, but really it's just chance. So really what I'm trying to talk about in this section is the statistical significance of this correlation coefficient. In other words, how sure am I, what is my level of confidence that there really is a linear relationship here and it's not just due to chance, just total like rolling the dice. I mean, I can roll a die and get 3 6s in a row. That's kind of unlikely, but it can happen. So the same sort of thing with these, the concepts here we're talking about with lots and lots of data points. So at what point are we able to say that we're, for instance, 95% sure that there is a linear relationship here? How do we actually figure that out? Because a lot of times your problem will be stated in such a way, and we're going to end up using hypothesis testing to figure that out. Notice I used the word level of confidence a minute ago. When you see level of confidence, definitely if you see level of significance, you need to be thinking that there's going to be a hypothesis testing probably in here somewhere. So what we're going to do is a hypothesis test, and we're going to test at some level of confidence, 95%, 92%, whatever. And our test is basically going to try to figure out, is there a linear relationship here or not? And when we get the answer to the hypothesis test, we'll be able to say that we're 95% sure that there is, or that we're 95% sure that there is not a linear relationship there. So we're going to do a hypothesis test. So what we call it is a significant linear relationship. Right? And you'll understand why in just a second. This is going to be a two-tail hypothesis test. I'm going to warn you that we're going to do this whole thing and I'm going to explain how to do this, and at the end of it you're going to be like, well, who cares? If the correlation coefficient is really big, close to 1, you know, I'm pretty darn sure these things are related to one another and they're linear. And that is true to an extent, but the hypothesis test puts an actual level of confidence number on it. When you do a study, you want to be able to tell them that you were this certain of the result. So you can't just collect data and say, oh, the correlation coefficient's high, we're done. You have to be able to prove mathematically that you're very sure within a certain level of confidence of the conclusion you're drawing. So that's why we have to put numbers to it. All right, now I want you to remember, I'm going to go ahead and write the null and alternate hypothesis down here, and we're going to talk about it. The null hypothesis for this test is going to be always the same thing. It's going to be that rho, which remember, rho is the correlation coefficient of the whole population, though, okay? We're going to say the null hypothesis is that rho is equal to 0. Now, what happens if rho is equal to 0? It's the same as if r is equal to 0. Now, r is just the correlation coefficient of my sample data. Rho is the correlation coefficient of the entire population that you have. So you never know what rho is. You can't calculate it because there's millions of people. But anyway, if rho is 0, then what you're saying is this implies no relationship. Remember those plots we did before with when it wasn't linear, it was just kind of random data everywhere? Well, that would be very likely to happen if you had the correlation coefficient equal to 0. So if that is what the null hypothesis is, then the alternate hypothesis has to be the opposite of that, which is that the correlation coefficient of the population is not equal to 0. And that implies, the arrow here means it implies a linear relationship. And specifically, it implies that we believe that there is a linear relationship here with a certain level of confidence. That's the only difference that this section is really adding, is that you're able to tag a level of confidence into your conclusion that there's some kind of linear relationship. I mean, you can look at this and say, oh, this looks linear, but it's all subjective. You're just looking at it and you're saying, yeah, that makes sense. What we're doing now is we're tagging it with an actual level of confidence. All right, notice that our null hypothesis is here and our alternate hypothesis is here. And I told you it was a two-tailed test, and now you can see why it's a two-tailed test, because the alternate hypothesis has a not equal sign in it, which, as you know, means two-tail test. All right, so we're going to perform a two-tailed test here. Let me go and shift up here a little bit, and we're going to continue writing a few things down. All right. Now, all of these hypothesis tests that we're going to do are going to basically be done the exact same way. So I'm going to list a few things here, just kind of like characteristics of what we're going to do for every single one of these problems. So let me kind of draw a little bit of a divider line here, and then underneath we're going to write down what we're going to use here. For every one of these tests, we're going to use the t-distribution. You should know now, by now in statistics, if you've done the hypothesis testing with me, sometimes we use the normal distribution, sometimes we use the t-distribution, sometimes we use the f-distribution, sometimes we use different distributions. And basically that work has been done by people before us that have figured out that in these regimes and this type of testing, this is the best type of distribution to use. I'm not going to prove to you why we're using the t-distribution. That goes into math beyond the scope of this class. But for every one of these, when you're testing the linearity of data and if they're dependent on one another and the correlation coefficient and all of that, you're going to use the t-distribution for all of them. All right? Now, remember, when you do hypothesis testing, you need to know what distribution you're using and you need to have a test statistic, right? A test statistic is the number you calculate from your sample data, and then you kind of compare that to the rejection region to see if you reject or fail to reject a null hypothesis, right? So the test statistic for this case, for all of these problems, is going to be the following. It's the t-distribution, so your test statistic is going to be a t, and it's going to equal the following. It's a little bit ugly, it's not too bad. R divided by, you're going to have 1 minus r squared divided by n minus 2, but on the denominator you're going to have a giant square root that's going to include everything there. So that's going to be your test statistic. I know it looks ugly, but essentially what's going to happen is you're going to have some data. You're going to have raw data. From that raw data, you're going to calculate the correlation coefficient. Notice I have r down here. That's because you can't calculate the correlation coefficient of the population. What you do is you sample, that's why we're using r here. We get the correlation coefficient of the data that we have, so that's the sample data, we calculate r. We know how many samples, n is how many samples in our set, And we use Excel or a calculator to find out what r is. Then you just crank through and calculate t. It's a very simple calculation. I know it has a square root and all that, but you put the numbers in, you calculate t. That's going to fall somewhere on the graph, on the bell-shaped graph that I'll draw here in a second. And then you just figure out if it's in the rejection region or not. And that's it. And look at our hypothesis. If we fail to reject the null hypothesis, if we fail to reject, then that means that the population correlation coefficient is 0, and that means there's no relationship. But if we get into a rejection region, then we reject the null hypothesis and we say that the correlation coefficient of the population is not equal to 0. So we're using the sample data here to figure out what the population's doing. So if we end up in a rejection region, we're going to say that this is why this does say there's a linear relationship, because the correlation coefficient is not 0. But remember, we're doing it all at a certain level of confidence. So you kind of already know from looking at it, or you kind of guess if there's a relationship there or not. But because we're doing the test at 90% level of confidence, you'll be able to state at 90% level of confidence, for instance, if there's a relationship there or not. Okay? All right, so we're going to be using the t-distribution. Here's going to be the test statistic. The other piece of information that you need to know that we're going to be using is that obviously the level of significance, which you need for all of these problems, is always alpha. We're going to be given that usually, or a level of confidence. We'll do 1 minus that to get the level of significance. The final piece of the final piece of information is the degree of freedom that we'll need. The degree of freedom for all of these problems is going to be n minus 2, the number of samples I have minus 2. So this is important. I wanted to put all of this down in one place because you're going to use all of this information to do all of these problems. So let's go and draw a quick picture of what we're actually going to do. So remember, this is a t-distribution, which looks very similar to a normal distribution. So let me go ahead and draw it here and show you what basically you're going to be doing. So here is our symmetric t-distribution. Looks something like this. And this should look really familiar, by the way, because we did lots of hypothesis testing in the t-distribution. Now notice that this is a two-tail test, so because of that, half of our level of significance will be in the right tail, and the other half of our level of significance will be in the left-hand tail. So what you need to do is draw a little picture, and I do this for every single one of these problems. That's a right tail. In this tail has an area of half of our level of significance, which is in this case alpha over 2. Whatever alpha is, if it's 0.05, you take that and divide by 2. That's the area over there, for instance. All right, now in the left-hand tail, you're going to have exactly the same situation. Go ahead and shade that guy, and the area in that left-hand tail is again going to be alpha over 2. So the sum of these two numbers, alpha over 2 times 2, should give you alpha. So your level of significance is going to be solely or divided up equally between those two tails. Now in the middle here, this is a symmetric distribution. So this is t is equal to 0 right here in the middle. And this value here, the value that gives you an area of alpha over 2 to the right, we label it in statistics t alpha over 2. And because it's symmetric about 0, this one is negative t alpha over 2. All this stuff should seem very familiar because we've done hypothesis testing with the t-distribution. And it's basically the same thing. You have your level of significance in the left and the right-hand tail, and the boundary regions that define your rejection region is going to be negative t alpha over 2, positive t alpha over 2. So basically, what's going to happen here is that in the next section, we're going to give a problem. We're going to get some data, and we're going to, first of all, draw this picture again. And we're going to have a level of significance that's going to be a number. We'll divide it by 2, and we'll say that this is the area over here. Then we'll have to find the value of t off the table in the back of your book that gives you this area to the right. In order to find that, you're going to need the degrees of freedom for your problem, which is just how many samples you have minus 2. So you literally flip to that table, find the proper table for that level of significance, go down however many samples minus 2 to that degree of freedom, and you read off the chart a value of t. That value of t gives you this area to the right, so that's going to be a number here. You're going to know this boundary here. And then the negative of that number will be the symmetric number on the other side. So then those are going to define your rejection regions. If you get a value of your test statistic from the data you have beyond this point to the right or beyond this point to the left in the negative sense, then you'll reject the null hypothesis. In that case, you will say that since you're rejecting this, you will then say the alternate hypothesis, the evidence supports the alternate hypothesis, which means that rho is not 0, which means that there exists a significant linear relationship between these two variables at that specific level of confidence. So not only will we think that there's a linear relationship, but the hypothesis test will tell us that we're 95% confident that it exists, for instance. Okay? And if the test statistic doesn't put us in this region or this region, if the test statistic falls anywhere in this white area here, then we're going to fail to reject that null hypothesis, which means that we're going to say this is true with this evidence anyway, and then we'll basically say that there's no relationship in the data. Now, I want to make a couple final comments. We're going to actually do one of these problems in the next section. It's going to become a lot more clear once we do it. But basically, what's going to end up happening is this test statistic is going to totally determine the outcome here, right? Let me go back and recenter ourselves with where we came from. I mean, you all know that if the data points lie very close to a line, that there should be, I mean, just from a gut feel, that there should be a linear relationship there. And the closer these dots are to the line, the stronger and the more confident we are that there is a linear relationship there. And if you have data points more dispersed, farther apart, you're not quite as sure. They could still be there, but you're just not quite as sure. If they're really close to that line, you're more and more sure. The closer they are to the line, the closer the correlation coefficient is to 1 or to -1. So when we go down here and do this hypothesis test, the bottom line is, look at how this test statistic is set up. The only thing in the numerator is r, the correlation coefficient. So that means forget about the denominator. Just pretend it doesn't exist. If you hold everything constant down there and just start increasing r, right, what's going to basically happen? If you increase r, what's going to end up happening is that the test statistic is going to increase. If you go through and you start thinking about this, as you increase r, this numerator is going to increase. Yeah, there's some stuff going on in the denominator, but when you go through the logic of it and think about it, when you increase r, the correlation coefficient, closer and closer and closer to 1, then this t-test statistic is going to get bigger and bigger and bigger. That means that if you take everything else and hold everything constant with the rejection regions, as r increases, the correlation coefficient increases, our test statistic gets bigger and bigger and bigger, closer and closer to a rejection region. Eventually, if we cross this line, then we say, no, this is not true anymore, and there must be a significant linear relationship between the variables, which is kind of exactly what we know by looking at those drawings. As the correlation coefficient gets bigger, the dots get closer and closer to the line, so we get more and more sure that there really is a relationship here. But don't forget that these boundaries here are governed by, the biggest thing they're governed by is the number of samples for sure, but the level of significance. So these goalposts, right, that you're trying to cross, they move, they float around based on what the level of significance is. So if you're more and more and more confident, you want to be more and more confident in the results, then the level of significance is going to be low, low, low. Like the smaller the level of significance, the higher the level of confidence, and this goalpost is going to move farther to the right. That means it's harder to conclude with a 99% level of confidence. Even for the same correlation coefficient, it gets harder and harder and harder to say that it's true when you start making yourself super, super confident in what you're trying to test. Okay. Now the other thing I'll say is I'll look on the flip side. Let's look at this test statistic and let's hold everything else constant. Let's hold the correlation coefficient constant. Let's say it's close to 1. So let's say its correlation coefficient is 0.9. That's pretty close to 1. If I saw a correlation coefficient 0.9, I'd be pretty confident there was a real relationship here between the two variables. But look at what's in the denominator. There is an r squared, and there is a square root. I know there's some other stuff there. But notice that in the bottom of this fraction down here, there's a number of samples. Yes, there's a -2, but essentially there's a number of samples. Okay? What happens if this correlation coefficient is close to 1, which means we're pretty confident in what's going on, right? Just from the back of the envelope. But let's say we start making the number of samples really, really small. So if you have 100 samples, you're going to be pretty sure of what's going on here. 50 samples, I'm still pretty sure. 10 samples, it's not too many samples. 5 samples, that's really low. 2 samples is crazy, right? Let's say you only have 2 or 3 samples here. As in the number of samples, if you're holding the correlation coefficient constant, let's say at 0.9, you start dropping the number of samples down to 2 and 3 and 4, then what's going to happen is the denominator of this fraction is going to get small, right? So if you look at this fraction here down on the bottom, if this number gets small, then this number, the whole fraction, gets big. When you divide by a small number, if you take the limit and make two samples here, then actually divide by 0, you get kind of infinity down here. But anyway, if you get smaller samples, this whole fraction actually gets bigger. And when you divide r, even though you're taking the square root, this is still making the bottom large when the number of samples gets small. So if you're holding this constant and you divide by a bigger number, what happens? It means t goes down. So you see what's happening? Even if I have a very high correlation coefficient of 0.8 or 0.9, I'm pretty darn sure of it. But then I only got that correlation coefficient by looking at 3 samples. Then that's going to drive t down and keep it close to the center down here. So even with a high correlation coefficient, I might not be confident in the results because I had such a small amount of samples. So you see, you have two things competing against each other. You have the correlation coefficient. Higher is better for saying that there's a linear relationship. And then you also have the number of samples in the bottom. Lower is not so good. So lower samples is fighting the higher correlation coefficient. Now if you go the other way and you say, well, if I have a high correlation coefficient with a high number of samples, like 100 samples or 1,000 samples, then I start to get really confident in what I'm doing, that the results are there. So I'm dividing by a big number here. That drives this whole fraction down small, so then I'm dividing this by a very small number, which makes t go really, really big. When you divide by small numbers, like if you divide by 0.2 or 0.3, you're going to get a large t, which is going to drive you in that rejection region, and you're going to start saying the alternate is true with very high level of confidence. So we're going to get into all these ideas again when we do a real problem, but I just wanted to tell you that's why the test statistic is constructed this way. It's taking into account the level of the correlation coefficient, but it's also taking into account how large your samples were, because obviously a great correlation coefficient with just 2 or 3 samples means nothing. If I go take a survey of 3 people and they all end up in a straight line, I'm going to get a really great correlation coefficient, but I'm not going to care about that data because it's only 3 people. It's not enough to give me a statistical weighting. So that's the hypothesis test, includes all of that information. So at the end of the day, you'll be able to say, I am 95% confident that there is a linear relationship between these variables because of all of these factors that I've taken into account. So follow me on to the next section. We're going to do a real problem, and we'll get some practice with the statistical significance of the correlation coefficient.